A particle travels along a semicircular path which has a radius of r from point A to point B. And what is the displacement and distance travelled? Well, the displacement is the change in position. So if we take our origin at A, the particle has displaced 2r units. And the distance travelled is the length of the path. So here we have a semicircle which has a circumference of pi r. So the correct answer is C. A position graph of a particle that's undergoing linear motion is shown. Which of the graphs best represents the velocity as a function of time? Well, here we see that the slope of the tangent to the curve is negative initially. So therefore the initial velocity is negative. So therefore the answer is either C or D. And because the position graph is relatively linear, up to this point, where the slope of the tangent to the curve is 0, the velocity is relatively constant and goes to 0 and then becomes positive. So given that the slope of the tangent to the curve is relatively linear, and therefore the velocity does not drop back down to 0, the correct answer is C. The acceleration of a particle is described by the following equation. And if the particle is initially at rest, determine how far it travels in the first 2 seconds. So given the acceleration is the change in velocity with respect to time, which is equal to 3t. So given this is a non-uniform acceleration problem, we separate the variables. So we have dv is equal to 3t dt, and integrate both sides. So given the particle is initially at rest, we integrate from 0 to some velocity v. And our reference time we take as 0 and integrate to some time t. So therefore the velocity as a function of time is equal to 3t squared on 2, evaluated from 0 to t, and that's equal to 3t squared on 2. And given the velocity is the rate of change of position with respect to time, and separating the variables, we have dx is 3t squared on 2 dt, and integrating both sides, we integrate from x0 being some initial position to x, and time 0 to a time of 2 seconds. So what we get is 3t cubed on 6, or t cubed on 2, evaluated from 0 to 2. So therefore, we end up with a displacement on the left hand side being x minus x0 is equal to 2 cubed on 2, which is 4 meters. So the correct answer is A. A pebble is dropped from a height h, and it travels the first half of the distance, being h on 2, in ta seconds, and the second half from h on 2 to h in tb seconds. And we're asked to find the value of tb on ta. Well, if we take our initial position at 0, we have the final position of h on 2 is equal to the initial position of 0 plus the initial velocity being 0 by TA as we drop the pebble from rest, plus 1/2 by the gravitational acceleration by TA squared. And similarly, we take our initial position of 0, so when the pebble ends up at height h, we have h is equal to 0 plus the initial velocity by time plus 1/2 by the gravitational acceleration by TA plus TB squared. So if we divide these two equations, we get 2 on the left hand side, and 1/2 g cancels, so we end up with TA plus TB all squared on TA squared. And if we take the square root of both sides, we have root 2 is equal to TA on TA, which is 1, plus TB on TA, and therefore the ratio TB on TA is root 2 minus 1. So B is the correct answer. The motion of a particle is described by the following equation. Find the acceleration at 2 seconds and the average acceleration between 0 and 2 seconds. So if we differentiate this expression, we have 3t squared plus 3 in units of meters per second. And if we differentiate again, we get the acceleration, which is 6t meters per second per second. So therefore the acceleration at 2 seconds is 12 meters per second squared, and the average acceleration is the change in velocity on the change in time. So at 2 seconds, the velocity is 15 meters per second, and at 0 seconds, the velocity is 3 meters per second, and delta t is 2 minus 0 seconds. So that gives 12 on 2, or 6 meters per second squared. So the correct answer is C. A helium balloon is released and floats to a height h with a constant acceleration a. Assuming that the total travel time is greater than 4 seconds, how much further does the balloon travel in the last 2 seconds than the first second? So if we designate this position as y equals 0, and this position is y equals h1, and this one is h2, and the final position is h, then we have an initial velocity of 0 because the balloon is released from this position. So therefore, using the kinematic equation, h1 is equal to the initial position plus the initial velocity by time plus 1/2 by the acceleration by a time of 1 second squared. And similarly, our next equation is h2 is the initial position plus the initial velocity by time, which is 0, plus 1/2 by the acceleration by delta t, which is t minus 2 minus 0 squared. And finally, our third equation is h is equal to 0 plus 0 by time plus 1/2 by a by t squared. Then in the last 2 seconds, the distance travelled is h minus h2. So we have 1/2 at squared minus 1/2 at squared minus 4at on 2, which is plus 2at, and minus 4a on 2, which is 2a. So that gives 2at minus 2a. And in the first second, we have the distance travelled is 1/2 by a. So therefore the difference in the distance travelled between this interval and the first interval, which we'll call delta y, is 2at minus 2a minus 1/2 a. And if we recognize 2 is 4 on 2, then we'll take out a on 2, and inside the brackets we have 4t minus 5. So a is incorrect because we have 4t minus 5 squared, and therefore the correct answer is B. A car is travelling horizontally at a velocity of 25 meters per second, and a bus is travelling ahead of the car at a velocity of 20 meters per second west. What is the speed of the car observed by a passenger on the bus? So we have the velocity of the car is equal to the velocity of the bus plus the velocity of the car relative to the bus, or as seen from a passenger sitting in the bus. So the velocity of the car and the bus are from the ground reference frame, or observed by a stationary observer. So the stationary observer will see the velocity of the car as 25 meters per second to the right, and the velocity of the bus is 20 meters per second to the left. And the velocity of the car observed from the bus is Vc relative to B in the horizontal direction. So therefore the speed of the car, being Vc relative to B, is equal to 25 minus negative 20, or 45 meters per second. So the car appears to be moving towards the bus at around twice the speed. And the correct answer is C, because the speed only has a magnitude and not a direction. A tennis ball is struck with the horizontal initial velocity. Ignoring air resistance and spin, what is the range R? So this is a projectile motion problem. And we're given variables of h being the height in the solution. So we'll just take this as h. And the tennis ball is only subjected to gravitational acceleration. So our projectile motion equation in the horizontal direction is the range being equal to the initial position plus the initial velocity by time. And in the vertical direction, we have our final position at y equals 0 is equal to the initial position plus the initial velocity in the vertical direction, which is 0, by time t. minus 1/2 by the gravitational acceleration by time t squared. So solving this equation for time t, we get t is equal to the square root of 2h on g, and therefore we get a range of v0 by root 2h on g. So the correct answer is D. A ball is thrown and follows a parabolic path. Assuming negligible air resistance, which statement is true? So first we have the acceleration of the ball is not constant, which is false, because we have a gravitational acceleration being constant in the surface of the Earth and negligible air resistance. And we have the speed of the ball is constant, which is also false, because if the ball is thrown at some initial velocity, then we have the speed at this point is equal to the square root of the component squared. So we have v0 x squared plus v0 y squared. So note that you can resolve this velocity into a horizontal and vertical component. Now as the ball reaches the peak of the trajectory, we have the horizontal velocity being constant, and the vertical component of velocity is 0, because there's no air resistance. So therefore the correct answer is D. A ball is launched from the ground with some initial velocity and a launch angle being theta, and lands on a platform at a height h and distance L. Derive an expression for h in terms of L, the gravitational acceleration, the launch angle, and the launch speed. So our kinematic equation for projectile motion in the horizontal direction is L is equal to the initial position of 0 plus the horizontal component of the launch velocity being v0 cosine theta by time t, and our kinematic equation in the vertical direction is our final position is equal to the initial y position of 0 plus the vertical component of the launch velocity being v0 sine theta by time t minus 1/2 by the gravitational acceleration by t squared. And now if we solve this first equation for time t, we have t is equal to L on v0 cosine theta, and then if we substitute for t into this equation, we get h is v0 sine theta by L on v0 cosine theta minus g on 2 by t squared, which is L squared, on v0 squared by cosine squared theta. And the v0's cancel, and sine theta on cosine theta is tan theta. So we have L tan theta minus GL squared on 2 v0 squared cosine squared theta. So the correct answer is A. These are the main 1D and 2D kinematic equations that you should know. And if you don't understand them fully, these topics are covered in the linked playlist below. So firstly, know the position vector, which is measured from the origin, and how to represent it in horizontal and vertical components. And the angle of the vector from the horizontal is obtained by taking the tan of this angle being equal to the vertical component on the horizontal component of the vector. And also understand how to sum two vectors. So for example, using the parallelogram rule or the head to tail method to obtain the resultant vector, and summing the horizontal components of two vectors A and B and their vertical components is another numerical method to obtain the resultant vector. And also understand the difference between the basic kinematic quantities, such as the displacement being the difference between the initial and final position in a given interval, and distance being the length of the path travelled. And understand which of these are scalars and vectors. And the average velocity being the displacement on a change in time, so it's an average over an interval of motion, whereas the instantaneous velocity is the velocity at a particular point in time. An average speed is distance on time, whereas instantaneous speed is the speed at a particular point in time. And similarly, you have average acceleration versus instantaneous acceleration, and instantaneous velocity versus instantaneous speed, where the instantaneous speed is the magnitude of the instantaneous velocity. So note that quantities like displacement, velocity, and acceleration are vectors, so they have a magnitude and direction, and quantities like distance and speed are scalar quantities, so they only have a length or a magnitude and no direction. And note some properties of the graphs of the kinematic quantities. So we have velocity is the rate of change of position with respect to time, and acceleration is the rate of change of velocity with respect to time. So the velocity is the slope of the tangent to the position time curve, and the acceleration is the slope of the tangent to the velocity time curve. And note the subscripts here, where we refer to the velocity and acceleration in the horizontal direction. And if you separate the variables and integrate these equations, we get the displacement over an interval is the area under the velocity time curve, and the change in velocity over an interval is the area under the acceleration time curve. And the distance can be obtained by integrating the speed over time. So it's the area under the speed time curve. So calculus here can be used to obtain the graphs of the position, velocity, and acceleration from each other. And these equations can be generally used where the acceleration is non-uniform. So for example, the acceleration can be a function of velocity, time, and so on. And in the case where the acceleration is constant, we have the following big five kinematic equations. So the first equation does not include the acceleration. The second equation does not include the displacement. The third equation does not include the final velocity. The fourth equation does not include time. And the fifth equation does not include the initial velocity. So know which equations to use based on the known variables and unknowns in a given problem. And in projectile motion, we assume the object is a particle under the influence of gravity alone. So you have one kinematic equation in the horizontal direction, and the same big five kinematic equations applied in the vertical direction, with the acceleration being the gravitational acceleration. And finally, we have the topic of relative motion, with the position of a particle A, typically measured from the ground or stationary reference frame, is equal to the position of a translating frame B plus the position of our particle A measured from the translating frame B, or relative to B. And if you differentiate this equation, we have the velocity of particle A being equal to the velocity of frame B plus the velocity of particle A measured by an observer in frame B. And similarly differentiating this again, you get the acceleration of our given object A is equal to the acceleration of the translating frame B plus the acceleration of object A relative to frame B. So in this area of kinematics, for translational motion, we treat objects as particles, so they have a mass, but we ignore their geometry. And once you've covered these topics adequately, using this brief revision and the playlist below to read up on these topics, then you can go on to the next quiz. If the area under both curves below is the same, which of the following kinematic quantities are identical? Well, remember that the velocity is the rate of change of position with respect to time. And if you separate the variables, so we have dx is vx dt, and integrate both sides, we have the quantity on the left hand side being the displacement, or change in position between two endpoints of a motion interval, and on the right hand side we have the area under the velocity time curve. So A looks like the correct answer, but we also recognize that the average velocity is the displacement on the change in time. So the average velocity is also the same in both cases. And therefore the correct answer is E. An object is falling under the influence of gravity and air drag. Which position time graph is consistent with the velocity function? Well, here we can see the slope of the velocity being the acceleration, which is the second derivative of position with respect to time, is less than 0 and approaches 0. And therefore the position time curve is concave down. And also because the velocity becomes constant as the time goes to infinity, then the position time curve becomes linear. So therefore the correct answer is A. If a car can accelerate from rest to a final speed v over a distance d, what speed can the car accelerate to from rest over a distance of 3d? And the acceleration of the car in both cases is A. Well, we have the velocity, the acceleration, and distance. So we can use v squared is equal to 0 squared plus 2 by the acceleration by the displacement over the interval. And our second equation will be v dash squared is 0 squared plus 2a by 3d. So therefore v is root 2ad and v dash is root 6ad. And if we divide them together, we have root 6 on root 2, and root 6 on root 2 is root 3. So v dash is root 3v. So the correct answer is C. If the acceleration of a car is 2t squared plus 1, what is the average acceleration in the interval between t equals 0 and t equals 3 seconds? Well, remember the average acceleration is the change in velocity on the change in time, and recall that the acceleration is the rate of change of velocity with respect to time. So if we separate the variables and integrate both sides from some initial velocity to v and a time of t0 to t, we have delta v on the left hand side. And dividing through by delta t, we have delta v on delta t is 1 on delta t, while the integral of the acceleration, which is 2t squared plus 1 with respect to time, and we're integrating from t equals 0 to t equals 3 seconds. So that'll give us the average acceleration. And therefore, 1 on delta t is 1 on 3 minus 0. And evaluating the integral, we have 2t cubed on 3 plus t, evaluated from 0 to 3. So therefore, we have 1/3 by 2/3 by 3 cubed plus 3. So we have 2 9s are 18 plus 3 is 21 on 3 gives 7 meters per second squared. So the correct answer is D. Two cars of the following initial velocities. What is the rate at which the distance between them is increasing? So if we have the velocity of car A being minus 3 to the left and 2 vertically, it looks something like this. And car B has a velocity of minus 2 to the left and minus 2 downwards. So the velocity of car A is equal to the velocity of car B plus the velocity of car A observed by a passenger sitting in car B, using our relative velocity equation. So therefore the velocity of car A relative to B is equal to VA minus VB. So minus 3 minus minus 2 gives minus 1 in the horizontal direction, and 2 minus negative 2 gives 4 in the vertical direction. So car A appears to be moving at a velocity of 1 meter per second to the left to an observer in car B, which makes sense. And car A appears to be moving vertically at a velocity of 4 meters per second to an observer in car B. But what we're looking for is the rate at which the distance between the cars is increasing, and distance is a scalar. So we take the magnitude of this velocity to get the speed. So therefore, we have the square root of minus 1 squared plus 4 squared, which is equal to root 17 meters per second. So the correct answer is A. Raindrops fall vertically downwards and hit the windscreen of a car that's travelling east at a velocity vc, and the speed of the raindrop observed by a passenger in the car is one of these answers. So if we take the velocity of the raindrop, that's equal to the velocity of the car plus the velocity of the raindrop observed by the passenger in the car, or relative to the car. So therefore, if we have the velocity of the raindrop as follows, then by vector addition, we have the velocity of the raindrop relative to the car as follows. So to a passenger in a car, the raindrop dropping vertically appears to be coming in at an angle to the windscreen. So by geometry, this angle theta is this angle over here. So we can solve this using trigonometry. So we have tan theta is the opposite edge on the adjacent edge, being the magnitudes of both velocities. So therefore the speed of the raindrop is equal to the speed of the car on tan theta, or VC cotangent theta. So the correct answer is B. Raindrops fall vertically and hit the windscreen of a car that's travelling east at some velocity VC. And what is the car accelerating at? So the car has some horizontal acceleration, and the raindrop is falling on the car under the influence of gravity. So it has an acceleration of g. And using the relative acceleration equation, the acceleration of the raindrop is the acceleration of the car plus the acceleration of the raindrop relative to the car, or observed by a passenger in the car. So by vector addition, we see that AC plus the acceleration of the raindrop relative to the car is equal to the acceleration of the raindrop. And this angle here of theta is equal to this angle. But let's solve this problem using the horizontal and vertical components of the acceleration. So in the horizontal direction, the raindrop has no acceleration because it's falling vertically, and we have the acceleration of the car being horizontal minus the magnitude of the acceleration of the raindrop relative to the car sine theta in the horizontal direction. And the vertical acceleration of the raindrop, which is downwards, is equal to the acceleration of the car in the vertical direction, which is 0, minus the magnitude of the acceleration of the raindrop relative to the car, cosine theta, to get the vertical component. So if we take the acceleration of the car to the left-hand side and divide the two expressions, we end up with the acceleration of the car on a gravitational acceleration is equal to sine theta on cosine theta. So therefore the acceleration of the car is g tan theta, and the car was travelling east. So therefore the correct answer is B. Which of the following projectiles takes the least time to fall back to the ground? So using the vertical kinematic equation, the vertical velocity at the top of the trajectory is 0, and that's equal to the y component of the launch velocity minus the gravitational acceleration by time. So the time only depends on the vertical component of the launch velocity and the gravitational acceleration. And we're asked for the projectile that takes the least time to fall back to the ground. So that's projectile 1, which will have the smallest vertical component of the launch velocity. So the correct answer is A. A projectile is launched at a velocity of v0 and an angle theta. What is the difference between a minimum speed and a maximum speed? Well, the launch velocity has the largest magnitude, and the launch speed is the magnitude of the launch velocity, which is a square root of v0 squared cosine squared theta plus v0 squared sine squared theta. And the velocity is the smallest at the top of the trajectory, as it only has the horizontal component, and the magnitude is the square root of v0 squared cosine squared theta. So the horizontal component remains constant throughout the flight of the projectile, assuming no air resistance. So using our trig identity, we end up with v0 minus v0 cosine theta, and therefore the difference between the two speeds is v0 by 1 minus cosine theta. So the correct answer is B. A ball is launched from a cliff, which is a height h above a lake, and the ball has an initial velocity v0 and a launch angle of theta from the horizontal. So the trajectory of the projectile will look something like this, being parabolic. What is the time taken for the ball to land in a lake? So we know the final position of the ball is at y equals 0, and that's equal to the initial position plus the vertical component of the launch velocity, which is v0 sine theta, by time t minus the gravitational acceleration by the time squared on 2. So doing a bit of algebra, we can multiply through by negative 2 on g. So we have 0 is t squared minus 2v0 sine theta on g multiply by t minus 2h on g. And now using the quadratic formula, we have the time of flight of the projectile is minus b, which is 2v0 by sine theta on g, plus or minus the square root of b squared, which is 4 by v0 squared by sine squared theta on g squared, minus 4 by a by c. So that will be plus 8h on g. And if we multiply this by g on g, we have the following expression. And that's all divided by 2, multiplied by a. And now we can do a bit of algebra. So we have t is v0 sine theta on g, where the 2's cancel, and plus or minus. And if we factor out 4 on g squared, we end up with a 2 outside, that cancels with the 2, and a g in a denominator. And in the square root, we have v0 squared by sine squared theta plus 2 gh. And because the time of flight is positive, then we take the positive root. And therefore the correct answer is A.